In this video, we'll talk about solving radical equations. So in my opinion, the best way to do these is just walk through a few examples. For the most part, you just follow your order of operations backwards, but there are a couple of caveats, a couple of pitfalls that we have to navigate. So first, let's say we wanted to solve for x in this equation. 5 equals the square root of x minus 2 minus 1. Well, if we think about what we did to x, we took x, we subtracted 2, we took the square root of that, then we subtracted 1, we got 5. So the logical first step to undoing those things would be to undo the minus 1. So we can do that by adding 1 to both sides. So 6 is going to equal the square root of x minus 2. And then I'm looking at it thinking, okay, let's undo the square. We can do that by, or the square root, we can do that by squaring both sides. So we can say this is 36 is equal to x minus 2. And then we can add 2 to both sides. 38 has to equal x. Now, sometimes with these, you get what's called an extraneous solution, and that is because a square root is only the inverse of a square for certain values of x, and sometimes it creates a weird extra solution. So what we have to do with this 38 is we have to plug it back in and verify that it does indeed work. That's our way of making sure that it is indeed a solution. So we're going to do 5, and we want to know if that's equal to the square root of 38 minus 2 minus 1. Well, square root of, or we take 38 minus 2, that's 36. We're going to square root that. So that would be 6. And 6 minus 1 does equal 5. So this solution does work. However, sometimes you'll check them and you'll get something completely bogus, like 7 equals 0, for instance. You'll get a non-true statement, which would mean that that value really isn't a solution. It just would be if squaring and square rooting were perfect inverses of each other, in terms of functions, I suppose. So let's look at another example. If we wanted to solve for z in this equation, the first thing we would do is subtract the 2 from both sides. So 4 times the square root of z is going to equal negative 2. And then we can divide by 4. So the square root of z is going to equal negative 2 over 4, which reduces to 1/2. And then we're going to square both sides. Okay, so then z is going to equal positive 1/4. Now let's check it before we move on. So we're going to have 2 plus 4 times the square root of 1/4, and we want to know if that's going to equal 0. Well, we'll have 2 plus, so we'll have to think about it, 4. The square root of a 4th would be 1/2. And we want to know if that equals 0. Well, 2 plus 2 does not equal 0. It's 4. So this, z equals 1/4, is an extraneous solution. So ultimately, how I would answer this question is that there is no solution. And sometimes you'll work it out and you'll get multiple answers, and the idea there is you'll have to check both of them. One of them may work, one of them may not. So we have to verify these solutions because sometimes they work and sometimes they don't, and it stems from this idea with squaring and square rooting, and especially when you're talking about negatives, sometimes weird things can occur. Okay, let's look at another example. This one's a little bit different. We have radicals on both sides of the equation. So we could try and subtract or add over the square root of x, but then there's no way to really bring it into the original radical, the x minus 12. So what if we square both sides of the equation? Now we have to be very careful here because we're looking at a binomial here on the right. The one on the left is pretty easy. We have a square root of an expression, which means that we're going to have whatever the expression is. Now this one's a little bit different because the radical's not over everything, it's just over the x. So this is going to equal 2 minus the square root of x in parentheses times 2 minus the square root of x. Now we can apply our smiley guy, the FOIL, the double distributive, whatever method you choose. We're going to now multiply the binomial and the binomial. So we'll take 2 times 2, which makes 4, square root of negative x times square root of negative, or negative square root of x times negative square root of x, which makes a positive x. Then we have 2 times the square root of x, or negative square root of x, so we'll have negative 2 square root of x, and another negative 2 square root of x. So this is going to turn into x minus 12 is equal to 4 plus x minus 4 times the square root of x. Now we can kind of apply our algebra skills. So let's subtract 4 from both sides and subtract x from both sides of the equation. Now you'll notice the x's are going to cancel out here, leaving us with negative 16 is going to equal negative 4 times the square root of x. Now we can divide by negative 4, which means that the square root of x is going to equal 4, and then we're going to square both sides again. So this would say x is equal to 16. Now again, we have to check this solution. And once we've done that and we verify that it does indeed work, then we know x equals 16 is a solution. So let's check it over here. We want to know about the square root of 16 minus 12. That'd be the left side here. Well, this would be 16 minus 12 is 4. Square root of 4 is 2. We want to see if we get the same thing on the right side, and I'll do that in green. So we're going to take 2 minus the square root of, in this case, 16. So 2 minus 4 is equal to negative 2. So in this case, again, we have another extraneous solution. So again, we have no solution here. So just be careful when you're going through with these. Make sure you check the solutions. It can be a bit tedious, but double check it, make sure it does indeed work, because it happens quite a bit where there is no solution, or if you have multiple solutions that only some of them actually work. So for the most part, you can treat these just like you would any other expression or any other equation. Just undo what you've done to x and just be very cautious how you go forward. It's also worth noting here that if we're trying to undo a cube root, we can do so through cubing and vice versa. So squaring and square rooting are inverse operations for the most part, and then we can also consider the same thing of cubing, cube rooting, so on and so forth with other radical powers. It's also worth reminding you that we can convert from fractional powers to roots. It's worthwhile to stay up on that. And if you haven't already, check out the video on rational exponents. Very, very helpful. So let's do one last example. Let's say we've got something like this. The fifth root of x cubed equals 7. So this is a very, very weird problem in the idea of, okay, how do I think about this? There's a couple ways you can go. The first would be to rewrite this as an exponential equation. So x to the power of 3/5 is equal to 7. And then I can think about, okay, what's going to make it to where this 3/5 becomes 1? Well, we're going to multiply by the reciprocal. Now, how I do that is by taking both sides to the power of the reciprocal, which in this case is 5/3. So then x is going to equal 7 to the power of 5/3. And we can run to a calculator and do that if we want to. We could rewrite it as a radical expression. So we could rewrite this as x is equal to the cube root of 7 to the 5th power. All of these, or both of these, are valid, assuming that they check out. And then we can also, if we go back to the beginning, we can go another route, and we can do this as a two-step equation. We can undo the radical. So we're taking x, we're cubing it, and then we're taking a 5th root. So we can say, all right, then x cubed has to equal 7 to the 5th power. And then likewise we take a cube root, so then x is going to equal the cube root of 7 to the 5th, which should look familiar. Now again, we'll have to plug this in to verify that it does work. But assuming that it checks out, this would be our solution. Whether you write it as an exponent or as a radical, both are equivalent, mathematically speaking.